So today is my talk is going to be about clustering of multiview data. But just I would like to say something. These two, the young two are two of my co-authors, plus Wes. Yesterday night they took me out drinking. So if I say something, Wes, I don't even know, but Wes is there. So if I say something fun, you know why. But it was actually a great night. So what are multiview data? Multiview data are data sets which basically collect different features, provide different information or representation on a set of subjects. Each view, the point is like each view provides a quite different, unique type of information on the phenomenon under study. Each view can be very different from each other and they can have very different support spaces. But when you put all this information together, you get a better understanding of the phenomenon you are interested in. You're interested in studying. And today the talk is about clustering subject based on multiview data, based on different views of the same set. So most of the example I will present, they come from this cohort study, which is a Singaporean cohort study, it's a very, very good cohort study instead, in the meaning that is richly phenotyped. It includes about 1,000 kids plus mothers, and they're interested in understanding the physical as well as mental development of the children. So I give you an example, multiview data. Here we have some trajectory for randomly selected kids. The most left panel presents the standardized BMI over, I think, 10 years of age. So you see those are the BMI trajectory. The central panel presents basically, it's a two-state Markov process. So these kids go through time from a normal and hypertensive state, and basically they move through time. And the third one is a wheezing episode, which is related to asthma, and is the number of wheezing episodes, which are basically their panel count data. And the reason why people are interested to study them together, because there is clinical evidence, that there are a strong relationship between these three conditions. So as I said, this talk is about clustering, and obviously we are here, so we are going to use Bayesian mixed models to try to cluster multiview data. So we have a standard mixed model where observations are assumed to have come to one of M population groups, each model by some parametric density. Now M can be either finite or infinite, and the density of each group is referred as a component and is weighted by the relative frequency in the population, so by some weight. So if you are in the parametric world, then you have M is finite, and then you can make inference in different way. Either you run your mixed model for different value of M, then you pick your favorite goodness of fit criteria, and then you choose M. Or you can treat M as random and make it object of inference, and then you have to do some fancy reversible jump to or any other MCMC scheme that allow transition across a dimension. So there have been, beside the reversible jump, there have been other proposals in the literature, some based on point process representation of mixed model, and then I think a marginal Gibbs sampler more recently, which was inspired by nonparametric idea. Now, if you are in the nonparametric world, then M is equal to infinite, and basically a priori the number of components, you assume an infinite number of components, and what you're interested is to make inference on the number of clusters in the sample. In this case, you are working with an infinite dimensional parameter space, because the mixing random measure usually assumes can be represented by a countable mixture of point masses, allocation tau h with weights WH. And you see here I put some of the most famous prior in the non-parametric world, which are the Dirichlet process, obviously, normalized complete random measure, or also some stick breaking prior. Now, if you want to do posterior inference, here you can resort to different sampling scheme, like marginal Gibbs sampler algorithm. They usually integrate out the random measure, and they resort to some Chinese restaurant representation. In this case, inference is limited to point estimate like the predicted distribution. Then there are conditional methods, so you can build some sort of a Gibbs sampler that encompasses the random measure P. And now you can perform full Bayesian inference. So we have the slide sampler by Maria, Jim, I don't know if they're here, and Steve Walker. And then or you have retrospective methods, or you have also some methods based on the truncation either of the prior or the posterior. So this is it. But what we did recently with Raffaele, we showed that there is a link between the parametric world and the parametric and the non-parametric mixture model. And simply we show that a finite mixture model is a realization of a stochastic process whose dimension is random but has an infinite dimensional support. And so we refer to this process as normalized independent finite point process. And this is not a name I approve, but Raffaele is far too long, but Raffaele likes it, so we left it. And we show that this is a very general class of prior for a finite mixture model with random number of components. The good thing about this construction is that allows for a quite efficient computation by either a marginal or conjugate block to keep sampler. So I'll try to give you the intuition of what we are doing. So we start with the standard hierarchical representation of a finite mixture model with random number of components. So you have the density of the data, which is a mixture. On the weights of the mixture, we set the standard Dirichlet prior. Then we assume that the location of the mixture are IID draws from some base measure P0, and then we put a prior also on the number of components. So this is a standard setup for finite mixture model with random number of components. Then we can re-represent this the same thing using the allocation vector C. So each CI tells me to which component observation I is assigned to. And then we can do the usual representation, give xi given ci comes from the specific component. And then on this, we assume that the C have the usual multinomial distribution. We weights W, which are the weights of the mixture. And on the weights, we have the usual Dirichlet prior and exactly the same as before. Then we can still represent this by associating to each observation its own specific parameter. And so we have that the distribution of xi given theta I is f that depends on theta I. And then we put our prior, on theta I, we put our prior p. Now p has this representation as a countable mixture of point masses. So since it's discrete, there are ties between the theta, and when two observations have the same theta, we say they belong to the same component. And then we have the usual Dirichlet prior on the weights, the usual base measure for the location, and then the prior on M. So here you just need to think about this. If you think about this, the law of my observation, the density of the population is basically random. Why is it random? Because the W are random, the tau are random, M is random, okay? So each realization of this measure basically gives me a different realization of the law of the population. So, and this is basically the basic idea, is by specifying at this point a different distribution for M, for tau, and for the weights, then you obtain a much larger class of distribution for your finite mixture model. So this is really the basic idea. And just to think about it even in more simpler terms, if you remember, the Dirichlet distribution can be obtained as a normalization of independent gamma random variable. So we can start thinking about the weights of the mixture. Instead of normalized weight, we can think about the unnormalized weight and start putting a different distribution start to assign different distribution to their normalized weight S. And if we do this, we can come up with a constructive definition of a finite mixture model with random number of components by thinking about it as by thinking about our mixing measure P as obtained by normalization of a finite point process. So you rewrite your random measure as a countable mixture, but instead of using the normalized weight, we look at it as in terms of a normalized weight S. Okay, so that's what we are going to do. Then we are going to assume that our normalized weight are basically are a finite point process whose law is given by the non-probability measure, the Janossi measure over there, which has two components. The first one is QM, which is a discrete probability function that basically tells me the number of points in the process, and has a probability, the probability that m is equal to 0 is actually 0. And then we have a density H defined on the positive real line, from which then we basically draw our normalized weight. Okay, so just this is the interpretation for, in case you are not familiar, of the Janossi measure. Basically is the probability that exactly m points of the process fall within infinitesimal interval. Okay, so this is the usual interpretation. So this is how the assumption on the normalized weight. Then the tau are still IID draws from some measure P0. The sequence of S and the tau are independent as usual. And then you can make posterior computation extremely efficient by an augmentation trick. And so this is just an example of the realization of a normalized independent finite point process. So you draw your location, then you draw your normalized weight, then you normalize them, and basically that's it. And if you assume as H, so as the distribution of the normalized jump, you assume the gamma distribution, you go back to the standard finite Dirichlet process. And then you can put a shifted Poisson distribution for the number of components. So what's the link to the non-parametric process? It can be shown that basically the posterior distribution of the normalized process is the superposition of two independent processes. One process that basically corresponds to allocated components, so components to which observation have been assigned to, and the other process instead is still an independent finite point process, which corresponds to the non-allocated components, so components to which we haven't assigned any observation. And it's this second process, which is the latent variable, that basically links the parametric to the non-parametric world. So as I said, this just a recap of what I said. I think we have shown that there is a link, this link between finite parametric and non-parametric approach allows us to, first of all, to specify a large class of prior for finite mixture models with random number of components. Also allows us to devise very efficient MCMC scheme for posterior inference. And now this type of construction will be the building block of what is basically the main focus of this talk, which is multiview data clustering. So just to start with what the data look like, we start with assuming that our feature are actually ordered. So you can think about longitudinal data where time is the order, or you can think about features that are ordered in terms of importance. And the point with multiview data, which is that each column X can represent a very different feature with very different support space. So in my example, at the beginning of this talk, the first X could be BMI trajectory over time. The second X could be transition from one state, from an hypertensive state to a normal state, and so on. So for the moment, all the features are ordered, okay? So this is what you want to do is to understand how the clustering of the subject evolves through the features. And then obviously we would like to do prediction. Maybe you want to predict new feature, or you want to predict new observation. So this is basically what you would like to do. Now, why can't you do just a standard classical BNP exchangeable mixture? I mean, you could plug in all your features together in a huge big vector Y, and then specify your favorite model-based clustering model, either like a mixture, Dirichlet process mixture, or maybe, I don't know, I find a mixture model with random number of components. You can do that, but as many people know, when the T is very large, basically standard clustering method, Bayesian non-parametric clustering method struggle. So first of all, there is the course of dimensionality. So points in high-dimensional space are quite far apart. Then there is actually dependence there is a lot of dependence of the clustering result on the dimension of each feature. So feature with larger support space tend to dominate. And you end up in the detecting only a global clustering structure. You do not really understand the contribution of each feature. You end up also with a lot of small clusters, which are very difficult to interpret. So basically, clustering in 9 dimensions is not that easy. And so in reality, what you want is not only, you don't want only a unique clustering structure, but you also want to understand how the clustering changes to the through the individuals and through the feature, and how this clustering structure evolves. So the first thing we did, assuming the order, was something very simple. We extended to finite mixture model the enriched setup by Sonia, Sarah, David, and so on, to the finite mixture model with random number of components. And the idea is very simple. You first cluster your individual based on the first feature, and then given the cluster on the same feature, then you recluster within outer cluster, you recluster the individual based on the second feature. Now, so basically, if two individuals are not clustered together on the first layer, they will never be clustered together on the second layer. So this is a quite restrictive assumption. But basically, just to summarize the model, you have a clustering, whatever is your favorite clustering model on the outer feature. And then you have the model for the second feature, which depends, I mean, I don't have a pointer, but basically which depends on the cluster assignment on the first layer. So this assumption, so just to give you an example, these are a WhatsApp, this is a data set on WhatsApp used during COVID. So these people were given a questionnaire over 7 days, and the answer was basically the type of question. There were 7 questions over 7 days, and the type of question was, how many messages did you receive about COVID today? How many messages did you forward? So these are zero inflated data. And here what we have done, we have first clustered the data based on the zero pattern in the answer. So this is our first layer. And then on the second layer, we have reclustered the individual based on the sampling distribution of the non-zero responses. So, but as I said, this type of construction is very restrictive because basically actually can happen that individual change clustering, some stay clustered together, some they get clustered together. So you want something a bit more flexible. And so what type of model for your distribution of the data you would like? First of all, you would like the standard exchangeability of your observation. So you would like a model that basically is invariant to swapping of the rows. And this is standard row exchangeability, which we always require. Then what we want, what we said is like changes the order of the feature actually changes the information of the data. And this is because we have assumed that our features are ordered by time or by importance. But as the talk goes on, I will relax this assumption. And then the last thing that we want, which is quite important, is that partial swapping of the rows changes the information of the data. And you might wonder, why do you want this? Why should we care about this? Because if we don't care about this, what happens is that if we don't make that assumption, if I've clustered my individuals, say, at time 1, then I want to cluster them at time 2. If I don't make that assumption, this implies that the probability of 2 individuals clustering together at time 2 is the same independently of the fact that if they were clustered together at time 1, while in reality, you would like in a perfect world that if you were clustered together at time 1, you would like to have a higher probability to be clustered together at time 2. And so, and basically, if you don't make this assumption of that the partial swapping of the rows change the information of the data, the information only travels across distribution. So you, from one layer to the other, you only transfer population level information like number of cluster, frequency of the cluster, but you don't get this property, which is actually quite desirable. So, and then also we would like our model of the data to have nice properties like Kolmogorov consistency and so on. So what we introduce is something that we call conditional partial exchangeability. And so the idea is actually quite simple. I cluster my observation at time 1. So all the different colors correspond to different clusters. Then I go at time 2 of feature 2, and I assume that individuals that were clustered together at time 1 are exchangeable, okay? But not necessarily if they were not clustered together at time 1. So this is our basically the property we require, which guarantees all the nice things I was talking, all the nice invariants I wanted before. And actually, this is a quite flexible construction, which encompasses extreme cases like the rich construction or the usual total exchangeability as limiting case. So by assuming this type of property, then we can actually perform what we call telescopic clustering. So we start with layer 1, and we've set up our favorite clustering method. This can be P, can have a Dirichlet process distribution, can be a finite mixed model with random number of components. You cluster the individual. Then at layer 2, given the clustering structure at layer 1, you assume that clustering, that observation that were clustered together at layer 1, they come from the same distribution. You see there is a PC over there. That means that that distribution depends on the clustering structure at layer 1. And now what you need to do is to set up a joint prior on this collection of random distribution P1 up to PK1, which is the number of clusters in layer 1. Okay, and then you recluster the individual. So the way we have done it, we have tried basically two prior for the collection of random distribution at layer 2. We've tried an hierarchical Dirichlet process, and then a construction of dependent mixture with random number of components, which basically extend a paper, a very famous paper by Garrett, Fernando, and David on temporal clustering. And basically, there is a positive probability to be in the same cluster as in layer 1. Otherwise, you will belong to a new cluster. So this is what we have done. And this is, I'm not going to go through all the theoretical details, but conditional partial exchangeability has nice theoretical properties, and it guarantees Kolmogorov consistency, can lead to some quite good computational schemes, and Bamelia gives us what we want, so that the probability that two individuals are clustered together at layer 2 is higher if they were clustered together at layer 1 than if they were not clustered together at layer 1, which is exactly what we wanted. This is also, as I said before, conditional partial exchangeability is also connected to different work. I think all these people are here. I think, I mean, they're all here, so we did some. So if I've forgotten somebody now, it would be really a disaster, but I think it's connected to all this literature. And obviously, I've been speaking about only 2 layers, but this construction can be extended to many layers, and actually can also be relaxed, because we can only assume, so instead of having all the feature ordered, we can assume that there is only one important feature, say X, and then we relate the other feature just to this main feature, okay? And so that we can sort of relax this assumption of ordering of the feature. So this is a simple example of the examples that I was talking about at the beginning, where the main feature is the BMI trajectory of these 1,000 children. And then we want to relate the clustering of the BMI trajectory to 2 different types of information: metabolite concentration of these children, measuring these children, and then pre-pregnancy BMI of the mother, plus the result of the test for gestational diabetes, which are all known to be a risk factor for obesity. Basically, you can see there are 5 main clusters for the trajectories. And then, I don't know if you can read the numbers, but basically we show that most of the kids refer to the same, say, normal cluster of the mother, except the one that are in the obese group, overweight group, which refer to a particular cluster of mothers which have higher BMI and higher risk and gestational diabetes. Same thing for the metabolite concentration. Most of the kids belong to the same cluster of metabolites concentration, except the obese kids. But as I said, can we eliminate? That's what we want. We want to eliminate the order completely, and then we can do that, and then try to basically have a clustering model for each multiview data, but then bring all this clustering information from each view together to get a consensus clustering. And we can do this by assuming that there is a latent partition of this individual, which determines in some way the clustering structure in each view. So the model is quite simple. So we start with at the bottom with the model for clustering assignment in the latent partition, and here we have used the standard Dirichlet multinomial Dirichlet model for cluster assignment. M is the usual prior, but you can put also Dirichlet process, whatever. This is just easier. Now, what is important is actually how we model the cluster assignment in each view. So Cij is the cluster assignment of individual I in view J. Now we assume that we connect cluster assignment, we link cluster assignment of each individual through views by assuming the cluster assignment of each individual depends on the same set of parameters across views. So here omega I1, omega IM is subject dependent. And then on this set of weights, we put a Dirichlet prior with parameter alpha plus an offset in correspondence of the component to which individual I is assigned within the latent partition, okay? So just to give you a very schematic representation of the model, so we have a latent cluster assignment, C0, which determines the prior of the prior of the clustering structure within each view. Then each view has its own model, can be anything, and an advantage of this construction, and then the algorithm here can be easily parallelizable, but then through the usual Bayes theorem, cluster assignment within each view informs back the latent cluster structure. And now this is machine learning, is called consensus clustering, but they do it in a completely different way. So this is the idea of the model. Obviously, the model depends on very different parameters, in particular this parameter alpha. We have some nice property, like this very basic figure has been done by Garrett. Usually my figure are much more, Andrea does them. But Garrett did this, which is, by the way, I think it's very clear. So alpha is the parameter of the cluster assignment in each view, which can be view dependent. And you can see that as alpha goes to increases, basically the weight of the cluster assignment, the strength or the influence of the cluster assignment in the latent partition decreases, and basically the two things become independent. On the left, you have the adjusted Rand index, and once again, as also alpha increases, basically the probability to have the same cluster assignment as in the latent partition goes to 0. So this is the thing. So this is my original example of BMI trajectory of the two-state Markov process in continuous time, from moving from a normal to a hypertensive state at the final count data, which actually we had modify a bit to allow for zero inflation. So this is the three very different model for each view. And then you can see what happens. The strongest signal is in BMI, is the 5 trajectory of BMI, 5 cluster of BMI, which sort of feeds back to the latent clustering assignment. The clustering structure is much less strong in the other two views, but still information from BMI gets transferred through the latent clustering structure to the other two views. And this is, I think, is called the waterfall plot, and basically tells you how the observation move between one clustering, say C0, to another view from C0, say, to C2, and C1 and C2, how the individual moves between cluster. I mean, it's quite fancy, but you can see most of individual stuck together across view. And these are just the mean trajectory within each cluster. So you can sort of interpret this cluster in terms of obesity and frequency of asthma, of wheezing episode. So just a small comment. Obviously, in my talk, I did alpha the same across view, but it can be view dependent. Now, the fact that you have a latent clustering structure is quite flexible because you can use the prior on the latent partition to introduce information by experts. So you can introduce expert opinion, and you can do it in very different way. For example, you can specify a prior on row 0, which is the partition in the latent view, proportional to some whatever is your favorite clustering, to any ePPF or whatever, times a term that depends on the distance. This is a proposal by Amy and David Dance, where times a term that basically depends on the distance between your partition and some expert partition. Or you, instead of that construction, you can use the informed proposal by Garrett and Fernando, or you can use the anchored prior by David Dahl. I mean, basically, you can use any setup you like to introduce information. Oh, okay, I'm being super fast. I finished, so I can finish my slide with calm. And yes, so I just want to say something slightly different at the end of this talk. Basically, there is some of the feature can be still quite high dimensional. So now I'm going to show you an example of a very, very high dimensional feature of basically images, which are, I think, 600 by 600 pixels. And so so when even each feature is quite high dimensional, you need to try to do something slightly different and a bit more computational efficient and scalable. So there's been a proposal by, I think David Danson was the first one to introduce this, to do model-based clustering, but instead of the original space of feature, on the distance between each observation. So now, instead of modeling the observation in the original space, we are going to model the distances in the original, we're going to model the distances between the original observation. And so you can come up with a model on the distances, okay? So what we did is basically to model the distances using specifying the likelihood for the distances that contains two different terms. The first term, so which we call cohesion, which is the red bit, models the distances within the same cluster. And so you have basically a mixture model over there for the distances within each cluster. Then you have a second term here, repulsion, which model the distances across cluster. Now, the second term we had to introduce, so that actually that allows us to identify the number of clusters in the data set. So F and G we set up as a gamma density. They have a nice theoretical justification of why use a gamma density in this setup, and I'm not gonna go on that. Still, you can cluster the observation, the original observation, and you can set a prior on the clustering. You can put, once again, whatever you like. We use the size bias prior because we wanted to control the number of cluster. We wanted a small cluster with very small, with very small number of individuals for reason that I'll explain later. But anyway, you can put any other cluster, clustering prior. If you do the setup, so if you use a standard, say, BNP prior, still computation can be quite expensive because you have to assign each individual to a cluster. So, and that to run in every individual, through all the individuals, sometimes can be still quite expensive. So what we did is something is to use a slightly different clustering prior. So just to remind you, if you use standard distance-based methods like k-means and k-medoids are quite fast and they are very scalable, right? So for example, the complexity of k-medoids is of that order, is k times n minus k to the square, Obviously, k-means is simply k and t, where n is the number of observation and t is the number of iteration, and k obviously is the number of cluster. So people use them in practice because they're very fast and they work in high dimension. I mean, they work in the sense they give you a result. But as you know, sometimes they don't perform very well when there is cluster overlap, and obviously we're Bayesian, we would like some uncertainty quantification. So Bayesian distance clustering is actually, obviously, is a bit less orthodox Bayes, and is a sort of an hybrid solution. But actually, we show that it's quite robust in application and can be actually computationally very efficient. And we basically come up with an algorithm that achieves the same complexity of k-means. How did we do that? So the problem with clustering is that the space of partition grows exponentially in n. I think you all know that. So when n is large, it's very difficult to explore all the space of possible partition. So what we do is to extend ideas of Voronoi oscillation, which is a construction in continuous spaces, to discrete space. And then we show that basically what we obtain is the model, the Bayesian equivalent of k-medoids. So this condition. So just to give you the idea of Voronoi oscillation. So Voronoi oscillation, as I said, is for continuous spaces. So you take centers, okay, and then you assign all your observation to the closest center, and then you get obviously a partition of the space. So what we did is something very similar to k-medoids. We picked some observation at random to be centers, and then we assign the remaining observation to the center which is closest in terms of a certain distance. That's it. Now, what's the computational advantage of this? That you don't move anymore on the space of partition, but you just have to pick some center. And that this is much more computationally efficient than exploring the entire space of partition. And because the medoid set is much smaller, as simple as that. And so once you have this construction, which is very fast, then you can actually do whatever you want. You can use it, you can model some of the feature in multiview data by using a model distance-based clustering. You can model all your feature with distance-based clustering. Basically, you can do really anything you like. And even if you do distance-based clustering of your views, you can do nested partition, like an enriched version of these things. Or you can do actually also like a joint tessellation model, so you allow for more flexibility. And in that case, you can specify a loss function that incorporates both the partition on one view and the partition on the other view. And then you end up in the setup of basically a generalized Bayes posterior. Okay, so you can do many things. So I'll just show you an example of this, which actually I find. So these are coins, and these are sunrise coins, which come from Myanmar, and they were minted between the 4th and the 9th century. Okay, and so these are images of coins, and what numismatists are interested in understanding, because that gives them ideas about economic policy of empires and also trade routes and things like that, is to identify coins that are struck from the same die. Okay, so usually what they do is to do it manually. And now if you think about it, we have a set of 500, more than 500 coins. If you have to do it manually, this corresponds to more than 500,000 visual comparison. So it's about 800 hours of visual comparison. You have to do this for both obverse and reverse of the coin. So it takes a lot of time. So what we did is to apply this kind of setup. So now every image is quite big, okay? So we did this, we did the Bayesian distance-based clustering, and basically we come up with a distance by using computer vision tools, which like convolutional neural network, Bose-Einstein distance, contour, all these kind of things that are known in computer vision. We come up with a distance, and then we can cluster the coins based on their obverse and reverse, and you come up with this clustering structure. Here you can see that basically you would like because obviously there are coins found everywhere in the region, the clustering will be, the cluster size will be quite small. And basically, this is it for my talk. So I've been even super fast. What is this? Okay. So I've been more than on time. So I hope I've convinced you that Bayesian mixed model, I think I need to convince this audience, are a very flexible tool. And I've spoken about conditional partial exchangeability, which is a quite nice requirement to cluster multiview data, which highlight both the global structure, clustering structure, as well as the contribution of each feature to the clustering. Actually, I would like to, a bit of advertisement. One thing that I'm very interested in is to do variable selection for clustering. And I think later on, Raffaele will present something that we are working on, and in case you are interested. And then basically my talk has been structured like from very restricted assumption to a much more flexible assumption up to where we don't require any order of the feature. And then I wanted to show something quite different, which is Bayesian distance clustering, because sometimes, I mean, you need to be scalable and you need to solve practical problems. So you need maybe a bit less orthodox solution, because, I mean, what else can you do? And basically, this is it. Thank you for listening. These are all my co-authors. Most of them are here. So just if you have any questions.
I don't know if it is working or not. Not working? Okay. So we have time for questions. We have 15 minutes for questions. Okay. Okay. It's working. I was not to switch it on. So questions for Maria? Nobody?
This is a very nice talk. In the original study that you were talking about, you mentioned that it was very carefully designed and phenotyped, and they had carefully picked out subjects and stuff like that. If you, for example, knew that you were going to build the model that you used, how would you design the study, or how would you change the design of the future study to be as informative as possible, given that you already know the model you're going to use?
This is a cohort study, so they said, I mean, actually, this study is particularly well designed, because this is, I mean, this is a cohort study and they measure everything in this case. So they really measure everything. This is, so this one is particularly well designed, but in general, the more you measure, the better it is, no?
That's fine.
Thank you. Okay, other questions? David?
Really interesting talk, Maria, thanks. Question about projected consistency. I think you mentioned it as a property. Do all the different variants of things you're talking about have projected consistency, or just some of them?
No, everything.
Awesome.
In this talk. I mean, not based on distance classing, well, yeah.
Okay, we do have time for more questions.
Sandra.
Tons of interesting ideas for him, of course, as always for me. You know, one question, the distance-based cluster is kind of fascinating because it's not the classic, you know, just use-based there on everything. You must have a lot of choices here. Distance measures, choice, and on and on and on. Do you have any guidance or intuition about what's good?
What's good? I mean, no, you're right. It's, the distance is determines everything. It's like the loss function. So yes, so it's problem specific. So I mean, here, to be honest, the most difficult thing was to come up with the distance for the images, because there is wear and tear and everything. I mean, this was a very difficult problem, because now I put in images with, of points that are quite well preserved, but for some of these points are destroyed. And that made a huge difference which components the distance we put. So it's very, very, very problem specific.
Is that the kind of problem where unless you pass to something, it's pretty much hopeless? Because it is too complex to be.
Yes, I mean, you need to do clustering in the original. I mean, unless maybe you are, every image is 600 by 600 pixels. So, people do standard things like the k-means and whatever, but we show that it's much worse than what we are doing. So 600 by 600, 500 images is not easy to get. These are not easy.
Very cool stuff.
May I ask you a question about the distance-based clustering? Can you go back to the slide? I mean, I was wondering about the revulsion term. Yes, this one. So you said that actually you can identify the clusters only if you have this term. So if you don't have this term, what happens?
You don't, I mean, we can identify the number of clusters we did back then. Basically, all the other papers, the fixed scale, but otherwise we don't, I mean, it's a mess. So either we end up with too many clusters or we put everybody together. So that's didn't work until we realized that. I mean, that if you also model across cluster distances, then you have much more information.
Okay, and I mean, alternatives to the gamma densities for the G? I mean, does it make sense?
So it makes sense because it's a really silly proposition. But basically, if your original data has a multivariate from a distribution, then you sort of end up with the gamma densities. That's why theoretical classification. But it works quite well, I think.
Okay, okay, thank you. Further questions or Friday?
Thank you. Again, now on this distance clustering, do you have a temperature parameter is related to the previous question? Do you have a temperature parameter here to set, or you take the distance as the amount?
I mean, altitude, I don't understand.
Yeah, it's a temperature part of the.
Oh, no,
distance.
yeah, no, to something this. I mean, in a way, I have the lambda k and
The parameter of the gamma, right?
And marginalize on campus. It's 1.6, and the other one is. So to make it fast.
But is not sensible to the choice of the parameter of the gamma, or you?
It's so the gamma is separato, one è fixed, density to the one I fix. But not as much as you would think. I mean, it's the main, I would say, loophole here is the choice of distance.
Okay, so I guess that we have more time for questions.
Yeah, hello. So I have a question here. So, in specific some applications, those DIJ may not be independent, right? So those items, the DIJ, so do you think that it's matters here in this basic Bayesian distance clustering? So I mean, seeing this form, you kind of assume that the product of the density
Yes.
Right, but I mean, they may not be, because those DHAs are from a distance matrix.
I mean, I understand what you mean, because obviously they are calculated, it's one individual, and then one individual by 600.
You think that's
It's quite advanced, that, it's quite advanced, it's very big enough experiment. So the only problem is, as people figure out, is the distance, because that's the dimensional function.
all right. But how about the sensitivity to the parameters in those gamma densities? The sensitivity to the choice of the branches in the gamma districts in Plenary.
So one is fixed, and we use some sort of empirical base to fix it. And the other one we put a prior and then, in my testing, the first is the one that we fix that is the most important. Very well empirical base where it's well.
Thank you.
We do have time for more questions? No? On the table?
Anyway, I think I learned more about us in this one out here in Kentucky. I'm curious about some of these very widely resistance matrices. And I wonder if you have some intuition on how this compares, for example, to ideas that relate to spectral features, meaning sort of cooperating with non-hashing of these matrices.
No, actually, I have investigated, but yes, there are some connections of that. I didn't see that. That's.
Okay, so this is your last occasion to raise your hand. Well, actually, we do have time. So if nobody is going to raise his hand, her hand, let's thank our plenary. Thank you.